Okay, so we're going to be looking at the next section here in chapter 13, and it's going to be looking specifically at different types of collisions, okay? And the main one that we're going to be looking at is going to be collisions that are elastic, okay? So there's plastic and then there's elastic. Now, when we have two things that collide with one another, what ends up happening is that there is a period where they kind of deform and then they go back to their original shape. And when they start going back to their original shape, that is called restitution. And there is a coefficient of restitution that we can determine based on the two materials that come in contact with one another. So sometimes you see these close-ups of when, in this case, it's a picture of a golf ball that is on the surface or the head of the golf club. And we can see that there, I mean, we know that in its non-deformed state, this would be a circular golf ball, but on the face, you're going to notice that it flattens out. So it deforms while it's actually in contact with the head. When it goes back to that original shape, that's what we call the restitution of it. And to find out what that value is, we use what we call the coefficient of restitution. So we'll see that come into play in just a little bit. Now, when we have a direct central impact collision, what we have is that the centers of gravity of the elements that are going to collide with one another are in line with one another, and their travel is on the same line of action. So as we see these two balls here, ball A and ball B, notice that this x-axis goes through what we would believe would be their geometric center, and then their velocities are, along that same line being horizontal. Now, this is before a collision occurs. So we have velocity A of that ball A and velocity B. We can see that A is greater than B, so it's going to catch up and collide with ball B. In the next picture here, you can see where as ball A is in contact during the collision with ball B, there is a deformation that occurs. And like I said, the deformation occurs, but once that deformation occurs, then they're going to start to separate and go back to their original shape. Okay. So that part where they go back to their original shape is called the period of restitution, and it's a ratio that we can calculate based on how quickly or what the before and after velocities actually are of each one of the bodies that are in contact with one another. And then once they separate again, you're going to notice that their motions will change, or their velocities will change, based on that collision. When we have collisions that are elastic, we say that their momentum is conserved. So what that means is that the momentum before the collision up here has to equal the momentum after the collision. So that's the equation that we see here. And it's going to be the second approach that we're going to be discussing tonight, which is going to be the conservation of linear momentum. Okay. Now, as you can see, the momentum before is going to be looking at the mass times velocity of each of the individual bodies that are going to collide. So we have the mass of A times the velocity of A plus the mass of B times the velocity of B. That's the before side, okay? It's going to be equal to, after the collision, it's going to be the mass of B times the velocity B prime. And that prime just means that it's the after effect of the collision. And then plus, this is a typo, the mass of A times the after velocity of A. Okay, so we add those two together. Um, so as we look here to calculate that coefficient of restitution, this is the equation, and we will be adding it to our equation sheet in just a bit. But it's worth noting that our coefficient of restitution will be values from 0 all the way to 1. And a plastic collision, which means that once they hit one another, they stick together, okay? And then they continue on together. That means that the coefficient of restitution is going to be 0, okay? So they're going to stay together. But if you have a perfectly elastic collision, then our coefficient of restitution is going to be 1. Okay. And that just means that they bounce right off of each other and there's really like no deformation, which isn't a practical amount or a practical value because we always know when there's an interaction, there'll always be a little bit, very slight if it's if it's there or when it's there, but there's usually not going to be no deformation. So getting a value of 1 is going to be very rare. Okay. So let's take this information and add what we need to our equation sheet that'll be helpful for the examples that we're going to be looking at next. So I'm going to go underneath my camera and I've got my equation sheet out here. So this was the information from section 13.3. Now I'm going to be looking at, I'll just write here, this is going to be section 13.4. Okay, so continuing on to the next section in this very same chapter. Now, here we are going to be identifying and using the approach of the conservation of linear momentum. Okay. And all that says is that the momentum before is always going to be equal to the momentum that we have after. Okay. So we're going to say the summation of the m times v's before are going to be equal to the summation of the m times v's, the momentums, and we're going to put a prime in back of it after. Okay. So just v is going to be our before, and v prime is going to be our after. And that's before the collision, after the collision. Okay. And we sum the momentums because when we have more than one body that's going to collide, there's going to be more than one momentum that we have to add on either side. Okay. Then when we want to calculate that coefficient of restitution, how do I want to write this? So, okay. And that has the variable lowercase cursive e, if you would. Okay. And e is going to be calculated using the velocity b prime, and this would be like a second body, like body A, body B, or ball A, ball B, as we saw earlier in the illustration, minus velocity of A prime. Now, because these are primes, these are going to be the after effects of a collision. So those are going to be on top in this equation, divided by velocity A minus velocity B. Okay. And these are going to be the befores. Okay. Now, because it's a before and after collision, during a collision, there's always going to be losses. Okay. Whether that's, we always say friction, right? There's going to be noise that's going to be involved. There's going to be heat dissipated. And so our before velocities will always be larger or more than the afters. So you can see here that our coefficient of restitution will always be less than 1 or a value between 0 and 1. Okay. Now, because it's velocity divided by velocity, the units here are obviously unitless. There are no units. And then the last item that I want to add here, and this doesn't really have to do with the concepts here in this chapter, but in our it's in one of the either the problems or the last example that we look at the next time we're together, we are going to need the change in energy. It's going to be equal to kinetic energy 1 minus kinetic energy 2. And so change in E is going to be, let's see, change in energy and T1, T2, we know to be kinetic energy, which are equal to 1/2 mv squared. So this is kinetic energy equal to. Okay. And again, that'll be not today's example anymore, but the next time we get together, we have a couple examples to do, and it'll be that one. Kind of looking forward. Okay, so this will round out the equation sheet for chapter 13. Okay, so now we can pull that aside and we're ready to look at our next sample problem, which is going to be 1318. I will put 1318 on its own recording, so I will stop our recording at